Welcome back. Today we're talking about the introduction to quadratics. So let's go ahead and take a look at some graphs. So here we've got the three graphs of functions that we've talked about this year: linear, quadratic, and exponential. Linear, y equals mx plus b, and it's going to make a line that we can see there. On the right hand side, we've got our exponential graphs where we've got y equals a times the base raised to the x power plus h being the constant, and that's going to make a curve. And in the middle, the one that we're talking about now, is a quadratic. It looks very similar to what we talked about when we learned polynomials. So we've got y equals ax squared plus bx plus c, and that's going to make a u-shaped graph, or better known as a parabola. Now let's go ahead and take a look at this as tables. So here we've got three tables. We're looking again at linear, exponential, quadratic tables. So we've got y equals 4x plus 8. So we can tell that that's a linear because every time we're going up by a constant, and in this case, this constant is plus 4. So each time that we do this, we get plus 4 to our table. For exponential, that means that we're taking that x value and that becomes the base of our exponent. So we're going to go 2 to the negative second power, then 2 to the negative first power, 2 to the 0 power, 2 to the first power, and 2 to the second power. So whatever that x value is, that's what we're substituting in for our exponent. For our quadratic, we can see that we have a very different shape here. So we can notice that the main thing in a table is that in a quadratic, our y values are going to end up being the same at some point because they're going to be making that U shape. In our linear, that's going to be making a line. It's going up 4 every time. For our exponential, again, we're going to be making that curve, and we're going to be taking 2 to the negative second, or 2 to the negative first, or 2 to the 0 power. So it's going to be creating that curve, and it's going to be going up as we make that base our exponent. For our quadratic, we know we're going to be making a U shape. So as we're plotting our points, we know that 2 of our points are going to be having the same y value as it makes that curve. So we can see that here represented in our table as negative 2, 4, and 0, 4. Now let's take a look at some real-life examples. So here in the real world scenarios, we're going to be comparing our linear to our quadratic. So our linear, a puppy weighs 12 pounds at 4 weeks and 20 pounds at 16 weeks. How much did the puppy weigh at birth? So again, we can use our slope-intercept form here, use our slope formula, y2 minus 1, y1 over x2 minus x1 to find the slope. And then we can use either one of our points to make point slope form and then make our line here. But either way, we're going to be creating a line because that puppy's weight is going to be going up as the puppy gets older. For our quadratic, we have the fireworks are set off upward from the deck of 7 feet off the ground. When will the firework reach the maximum height? So again, we're going to be shooting this firework up into the air, but it's going to be coming back down because gravity. So as we shoot the firework up, it's going to reach its apex, and then it's going to be coming back down, and it's going to be making a curve. The curve steepness will depend on where you're shooting the firework, but hopefully you're not shooting it directly over your head, so the curve isn't too steep. And of course, with wind, it's going to push that away from you as well. Now let's talk about how to make the line of best fit and curve of best fit. So when deciding to use line or curve of best fit, remember a line of curve of best fit shows us the general trend of the data given. We can use a line or curve to make predictions about that data. So first, we're going to create a table with our points, and we can see that our linear line, we've used this one before in our Desmos calculator, is y1 approximately, because again, we're not sure, this is just a guesstimate. All right, mx1 plus b. For our quadratic curve, we're going to y1 approximate ax squared 1 plus bx1 plus c. So now let's take a look at that with our example. So here it says Alex is a golfer and he's decided to measure the height of his golf ball after he hits it in order to compare it to other players, which real golfers will do in order to determine the best place to hit the ball, for how high, for how long, in order to do better on the course. Alex measured the height of his golf ball in feet over time in seconds, and the data he came up with is below. Find an equation for the line of best fit, or in this case, a curve of best fit. So we're going to create the curve of best fit by using our Desmos calculator. We're going to create a table of values, and then we're going to enter the equation y approximate ax squared plus bx plus c. So let's do that now. And we're back. So you can see that I took out my Desmos calculator, I typed all the points into my table, and then I typed my equation in, and I got the parameters there of negative 15.714a for A, 63.0571 for B, and 0.17 for C. So now I can use those to write my equation. So my equation, I'm going to round to the nearest hundredth because again, these decimals are going to go on for a while, so I'm going to round. But we should have y is equal to negative 15.71 x squared plus 63.06x plus 0.17. So I went to my Desmos calculator, I made the table, and then I had to type my equation into a separate line to generate my parameters for A, B, and C, and then I knew where to plug those into my equation. Now let's use this information to answer more questions. So it says, using the equation from the previous slide, answer the following questions. So it says, if x represents the time the ball was in the air and y is the height of the ball, use the curve of best fit to estimate the height of the ball after 1.5 seconds. So we can look at our table and see that we don't have 1.5, so we're going to have to estimate that using the curve of best fit. So if I'm looking at my graph, I can see that it goes from 0 to 5 across the bottom, and it's going up tens every single time on the y's. So if I go over to about 1.5 and I go up until I hit 1.5, I can see that, oh, there it is, 1.5 is going to equal 59.4. I can also just place my point along the curve of best fit until I see my x value is 1.5. So I don't have to guesstimate, I have to make sure that I get my point along that curve. Now it will be a guesstimate because it is a curve of best fit, it's not exact, but we can use this curve of best fit to find our answer. So in this case, it's going to be 59.4, and we were talking about feet. Now let's take a look at the next example. So the next example says, using the equation from the previous slide, answer the following questions. So it says, using the curve of best fit, estimate how long it will take for the ball to hit the ground again. Round your answer to the nearest hundredth. So again, if we're looking for the ball to be hitting the ground, it's going to be coming down where our line is going to be on the ground, or in this case, our x-axis. So we can see the ball goes up and down, and we can see that it's going to be very close to 4 if we're looking there at our graph, but it's not going to be exactly 4. And we know it's not going to be exactly 4 because if we're looking at our graph here, we can see that it says at 4 seconds, it's still 2 feet in the air. So if it's still 2 feet in the air, then it can't be exactly 4. Now it's going to come down pretty quickly after that. It is a ball. It's probably moving pretty quick because it falls to the ground. All right, so it's going to be just a decimal, just a little bit past 4. And in this case, we can look at that we've done that. We've dragged our line to that point on the graph when it would be 0. And we see that it is going to be 4.015. And that's going to be seconds because, again, this was taken in time by seconds. Now let's take a look at the last example. So here in our last example, it says, using the table on what the previous slide, what is the maximum height the ball can reach in the air? So this time we're not going to look at our graph because that's got the curve of best fit and won't necessarily tell us where the highest point is. But looking at the table, we can. So we can see that we've gone to 0, 0, then 147, then 266, so it's still going up. But then it goes down with 345, so we know that it then dropped. So our maximum value is where it's going to be at the apex, and in this case that's 266, so it's going to be 66 feet in the air. That brings us to the end of this question. It also brings us to the end of this video and this set of notes. If you like this video, go ahead and throw us a thumbs up. If you love this video, go ahead and throw us a sub, and we will catch you in the next one.